calculate the motor, I missed that part. The motor power that we will need, I use the formula of force is equal to the velocity times the, no, I'm sorry, the watts power, velocity times the force we will need, or the force applied, and it delivered me that the ideal motor that we will need to use is per 60 to 80 watts, more or less.
Also having a calculation also for the lift, we use motor. We decided to use especially the Este motor because we don't need to move so fast, but also we can be precise of the time of the different the time movement of the bolt, so we can calculate this distance by the time. So we have the complete torque and force required to move only a certain part of the mechanism, so we cannot activate the damping mechanism. So that would help.
Okay guys, time is over now. Thank you so much for your presentation. And let's move to the next session, that's the question and answer. So please, any of you?
I have two quick questions. The first one, three quick questions. The first one is if you can go back to the materials slide, what was kind of the process to come up with those materials? That's one. Second one, the model, the 3D, is that based on, did you simulate it in any software, or did you just have that prototype based on initial measurements? That's the second one. And third one, you say power equals to force times what?
Times velocity, the velocity I require, and I can't remember if it is weight, but I found the equation.
Okay.
Yeah, but let me see it.
Is it not torque times angular velocity, or which is? Or,
No,
I mean, eventually torque is related to torque.
That we're related. It's more related with the lift thing.
Okay, but it's for that particular application, not the
That's
torque of
yeah,
the
no.
shaft.
Yeah, exactly.
Okay.
To answer your first questions of the materials, our priority was actually to have cost-effective as well as light, because our scissor arms will have to carry all that weight, as well as the base of our system, as well as the AGV. So it was like adding up the weights, and it was gonna cost us, well, we would have to use more voltage and more energy to move the system, as well as, you know, it could be more expensive. So we kind of like 5 kilograms is like 2 bags of beans. So we were like, okay, like cardboard for the walls of the lifting table could actually do it. Like it's not gonna hold that much, and if we actually need extra support, we could look at like corrugated cardboard, like a little bit stronger, as well as the nylon. We were like, it's gonna be like, it's more accessible for us to 3D print it. That way we actually like, we already have to do the SolidWorks part, right? Like we have to do the stress analysis, and that's gonna help us. So we might as well 3D print it. That's gonna save us time as well. And we did the stress analysis, and we actually we have a range of yield strength. I didn't mention that, but in order to calculate the area, we used the smallest yield strength, which was 40 megapascals in this, because that was gonna give us the maximum area that we actually have to use. Because if we use the 100 megapascals, it's going to give us smaller, and it was a bad estimate. So we were sure of that, and we decided with the calculations, nylon was a good source, and we also thought that because of the center of mass, yeah. For the center of mass, as it's rising, the center of mass is also going upwards, and that's a danger for our stability. And we are thinking that if it's necessary, based on our following like continuous like calculations and what we learned, we could actually do the scissor arms from the bottom to be denser, so the center of mass moves downwards, and we actually decrease like the risk of it going to the other way. And the base, we didn't choose really a material, but we're thinking of doing something really light as well. If we can do like MDF, probably depending on the weight, like really sticking to the light materials and accessibility of that.
Alright, thank you.
And the second question, right? Which was
The mechanism, do you use any software or how do you come up with the?
We searched for a prototype since we didn't have like enough time to make it, but afterwards we obviously will design everything. Like we already got the measurements, but still.
Also, we decided to use this model not only because we need to precise exemplify the central mass, but also this thing that will be at the base, so that will move so or lift will be up and down.
Okay.
it's mostly so
that's
we
why.
can visualize it.
But basically, this would be the prototype. I mean, with the adjusted dimensions and adjusted whatever.
And the extra
But the,
sensors.
but that's the principle of operation.
Yeah.
It looks like that.
It will look like that.
Okay.
Exactly.
It would be interesting, just a recommendation for the final presentation, bring that
Okay.
and show us how the initial thinking was and then the final prototype. How was it?
Yeah. That would be great.
Because
That's
this one is just their first approach, right?
Yes,
So
yes.
they need like to compare with kind of,
Sounds good.
right? Thank you.
I'm good.
Right, Mr. Sosa, please.
Okay, do you consider the factor of safety?
Yes, we did. That's this equation actually. We consider a factor of safety of 2 because we didn't actually need to lift that much, you know. And factor of safety is bulk area over the yield strength. And then if we do the calculation, the factor of safety will be yield strength over the allowable yield stress, which is actually this one. And then that transforms if we do a factor of 2 times allowable stress equals yield stress. Yes. So then we simplify the equation to show it this way, but we are using the yield stress, the factor of safety.
What about the profile of the links of the scissor mechanism profile? It's a rectangular profile, it's a hollow bar, a circular bar. Well, do you define the
It would be rectangular. Wait.
cross-sectional area?
Yes.
It's in it's in one of our diagrams. Look at you know. Look up. This one. Here. So it's a rectangle. 3 times 3 times 2.6, and it's not hollow. It's all filled out. But that will change with the classes that we take on this day forward. But that's the assumption that we made a rectangle.
Okay, do you base this profile according to a commercial material?
Since we were planning on 3D printing it, we didn't like that. We could do any shape we wanted, but we chose a rectangle because that way with the bolts you can connect it like easier. So
Okay.
that's why we chose a rectangle.
Finally, I didn't understand the relation. I mean, you calculate the force necessary to lift the mechanism. You're gonna use a motor, so you have to determine the torque and how is gonna be this relation between force and torque. What is the formula?
We forgot to put it here, but it's force times the radius of the screw. So here we calculated the revolutions per minute that we needed for like to move it and like to see which type of motor was best for us to use. Like we could have used like a reducer, but it was like it still had too many revolutions per minute. So we would have to make another system, like maybe like
An infinite screw in another gear to produce
Yes.
it. But to answer this simulates the torque question that you asked because we have the force we calculated with my code. We calculated all the internal and external forces, and so then the force to calculate the torque, we just have to divide it by the radius of the screw, which we did to kind of get an idea of what we needed from the other motors.
Okay. Thanks.
Okay, so we ran out of time. Sorry about that, but please take note of all of the suggestions, observations, considerations that the teacher just had asked you, and then please take this into account, and also for a comparison, as Guillermo said, for the last day presentation. That's at the end of the semester. Okay, thank you so much.
Thank you.
Have a nice day.
Good job.